Hi and welcome to the webinar. Today's webinar is how Isomil can cut your secondary grinding energy in half. Our presenter is Jon Burnett. To ask a question, just use the Q&A button at the bottom of your screen. Ignore the raise hand icon. We'll send you a copy of the presentation in a few days after the webinar. And of course, feel free, if you have questions at the end, to stay a little bit longer. Even though the webinar itself will finish, we'll stay live on air answering some remaining questions. We hope you enjoy this webinar.
Thank you very much, Stephen, for that very kind introduction. Now, it's my absolute pleasure to take you through this webinar. What I'd like to discuss today is I want to take you through the journey of how the Isomil has evolved into coarse grinding applications and give you a little bit of detail on some of the work we did in Stawell in Manitoba on how we were able to put an M100 in a secondary grinding duty and show some pretty remarkable results. Now, the Isomil is not a new technology. It's coming close to 30 years now, but it's got a pretty big install base. We've had 152 of these around the world, and over that time we have modified them to improve performance, reduce costs, and generally make a much more improved product. The mill itself can take feed up to 850 microns now with F100s of 3 mil. That is a bit of a step change from what you may be used to, and this is driven mostly from the new advancements in media that's on the market. Relative to other mills, we use lower SG media. The Isomil has about a peak performance of 3.7, 3.8 SG media. We don't see the efficiency gains with that higher SG, more expensive ceramic media. The mill itself is horizontal. That means you can start the mill fully loaded and you have enough breakaway torque where you don't have to dump the charge, which makes things safer. And there's no working under loads, no working at heights. It's got a tight size particle distribution, which I will touch on in a little bit, but it produces a much sharper product compared to our competitors, and quite proudly it scales up 1:1, and that's through the very conclusive signature plot test work that we conduct. Now, those that may not know, this is an example of a mill here on the left hand side. That mill works as follows. We pump slurry in about 150 kPa. It enters a sealed vessel from atmosphere. In that vessel we have a series of discs on a fixed speed shaft. That shaft turns, creating a tip speed within the discs of around 18 to 22 meters per second. What happens there is it fluidizes a bed of ceramic media and creates a highly attrition grinding environment. As the slurry is pumped in, you'll notice there are centrifugal forces, and what that will do is push your coarser particles out and your fines towards the center, meaning anything coarse will be preferentially ground before it leaves the mill. As you get towards the end of the mill, you'll notice that there's this yellow device there called a rotor, and what that is it's an internal classification device. The gap between that 8th disc and the rotor is much shorter than the others, and this is done deliberately. What it does is it creates forces that pushes slurry out to the edges, and that rotor acts as a pump along the outside of the mill. So what you're seeing is anything that moves out to the edges in the mill will have to be preferentially ground before it can leave the mill. This is what allows you to have that much tighter particle size distribution as you would against other stirred mills on the market. So that's a bit of the background, and let's go through a bit of the story. The traditional application of the Isomil goes back to the history of the Isomil. The Isomil was originally developed for a problem, and that problem was a 7 micron liberation grind target. Back in the late 1980s in Mount Isa, they recognized that they had to grind to 7 micron. At the time, they thought, let's see what technologies are out there. Let's give it a go. And what they found was, using conventional technologies at the time, such as tower mills and ball mills, they found that you required an extraordinary amount of power to get to 7 micron, and that when you actually got to 7 micron, the influence of steel media actually created a significant problem with the flotation results. What happened was iron hydroxide forms on the surface of the particles and damaged grade and recovery. So what they did was they looked outside of the business worked with our partners at Netsch, and we developed the IsaMill, which we successfully installed in 1994. That duty was a regrind application, which you can see here in a typical flow sheet. I've used the Jameson concentrator as an example. Now, since we installed it back in 1994, that was predominantly the install base in regrind duties and in pre-leach grinds. However, that was a long time ago and things change. We know mills are getting bigger and we know media is getting bigger. So why can't we expand our scope? There's no reason why not. If you look at the industry today, we recognize that comminution circuits are the largest single consumer of energy on a site, with up to 25% of the energy going into comminution circuits. That's a lot. In previous studies, I know in 2006, 2008, Anglo piloted a HPGR IsaMill circuit and it theoretically reduced specific energy by 17% relative to other circuits. We know in regrind mill trade-offs, when you look at the ball mill versus the IsaMill, you can save up to about 29%, not including the cyclone feed pump. So we know stirred milling is more efficient in certain duties. So what is stopping us moving it in circuit? And to do so, you have to do so in a stepwise manner. We're not going to move to primary grinding in a mill without slowly, methodically ensuring we get it right. Now, there's a big push on coarse particle flotation at the moment. The IsaMill can grind that. We've proven it. This is not new. With 6mm media, we know we can grind CPF concentrates. And to help further demonstrate that, I've used two signature plots. We have a single stage and a series grind. The single stage was taking about a 450, 500 micron concentrate down to about 30. The series grind was taking about the same, down to 10 microns. As you can see on a signature plot graph, where your size is on the bottom, your specific energy is on the side, it's a very linear relationship with good correlations. So the IsaMill can do that, and that's 500 microns, which is already a little bit of a step, but let's really have a go, let's really try to push it. So what I really wanted to touch on is, why is this all happening now? And the fundamental difference between the two was those previous signature plots used 6mm media. There is much larger media on the market today. So if you look on the right hand side, this is a photo of my desk with the view, and you can see that there's the media changing throughout the different sizes. In the far left, we have 2mm media. In the middle, second from that, about 5mm. And then across from that, we have 10mm media and 24mm media. And this is all rolled media. And as you can see, it's getting more competent, it's getting larger, and it's going to last longer. So if we're going to go to coarser particles, we have a bigger hammer to break those particles. But do we have the mill to do it? And Wes, and that's actually true, we do. So as you can see here on the left, over the last couple of years, we spent a lot of effort making the mills bigger. We've developed the M20,000 with a 5 or 5 megawatt motor. We've got an M30,000 with a 6 megawatt motor, and we have the M50,000. Mills are getting bigger. Media is getting bigger. Isn't the next logical step to move the IsaMill for bigger feed? We've got the media, we've got the mill. Why not? And this was the whole concept behind the secondary grind trial in Manitoba. And that has really prompted us with the new circuit design of the future. And to me, this is it. Here you have primary grinding going to an IsaMill and secondary grinding duty, similar to the test work I'm about to show. We have a coarse particle flotation unit, which is an area we're doing a lot of R&D in. Con from that feeds a fine scalper. The con from that is your final concentrate. Your tails get reground through an IsaMill in a traditional duty, through a Jameson cell cleaning circuit. And that, to me, is the concentrate of the future, and this is an area we're really pursuing quickly. So, I've kind of laid the groundwork, right? Mills are bigger. Media is bigger. I have the concept. How do I actually test it? And this is what I really wanted to demonstrate through this webinar. To test this sort of concept in the current configuration, to ensure that one-to-one scale-up, we actually have to move an M100. An M100 is a smaller IsaMill. It's the smallest one of our commercial mills. And that allows us to use 8 to 14mm media. In a lab, there is a issue with the larger media because you have to maintain a gap between the disc and the shell of 5 times your largest media diameter. This is all to ensure that you maintain fluidized behavior and you get an accurate energy reading. So if I can't use more than 6 mil media in the lab, I'm going to have to use this on site. So what we do is we move this to site, we take a feed, we feed that through the mill with varying media loads, and then from there we can develop a signature plot. And from that, we can compare to how the existing installations are running or a new concept. And this is what we did at Hudbay. So let's go through the trial that we presented a paper on back at CIM, and this will hopefully provide some questions. Hopefully I'll give you some answers. And as we go through it, I really want to say the whole purpose of this trial was to demonstrate proof of concept, garner interest, and if you actually want us to do a trial on your site, please reach out. So let us begin. In Manitoba, 2 metallurgists, myself and one of my colleagues, attended the Stawell mill. Our purpose of that visit was to conduct a proof of concept grinding test in a secondary grinding application, and we wanted to evaluate some of the larger medias. We wanted to evaluate 8mm 3.8 SG media, 8mm 4.5 SG media, and 10mm 3.8 SG media. Now, you'll notice why would you want to do 3.8 and 4.5 when I specifically said that we use lower SG media to our competitors? The purpose of that is all to do with reduction ratios. We wanted to evaluate whether the higher SG media could provide a higher reduction ratio in efficiency. The rule of thumb we typically use is a reduction ratio of 8 per media type. We were trying to expand it and see if we could do this in a course of duty here. Sorry. Those that don't know, this is the Hudbay Stawell mill circuit. I just want to take you through a bit of a run through on it. So up here we have the Stawell rod mill and ball mill circuit fed from 2 fine ore bins. There's also the chisel circuit that they also grind the feed for flotation. We have a pre-float. We have a pre-float circuit that removes the talc, followed by a copper rougher circuit and a zinc rougher. We've recently spent a bit of time there because we put some Jameson cells in. As you can see it in the talc recleaner, the copper rougher, copper cleaner, zinc rougher, zinc cleaner. And that circuit, very, very efficient, but it also allowed us the opportunity to test this concept. So, circuit, very quickly. So where did we do our work? We actually did it on the Stawell rod mill discharge. So what we did was we sampled a feed on the discharge pan, and that fed directly to the M100 through gravity. As you can see, this was the installation. I will admit, it's not the most ideal sample source, but like I said, this is proof of concept. Let's see what we can do with what we have. That line fed via gravity all the way into the mill. As you can see here, we had the isolation valve, 2 flushing ports, goes through into the mill, sample point at the mill, directly into the feed end, through the mill, out the discharge to the floor where we recovered it via sump. And we did that with various media loads and concurrently sampled the ball mill that it was taking the same feed at the time. So how did it go? That's a very good question. So we learned a lot. We learned a lot of what the mill was capable of and what we had to change. So with the 8mm results, we learned 2 things. At a higher rotation speed, higher tip speed, we noticed that the energy consumption was much more substantial versus the lower tip speed. That made us think. But when you think of the internal classification device, it makes more sense because you're retaining more media because there's a much faster back current in the mill. For the lower feed, 30 Hertz feeds, we noticed that at 10 kilowatt hours per ton, similar to the existing installation, we were able to produce a much sharper product size distribution, which is what we expected, and we were much more efficient on the fines. Now, 8mm was great, produced the concept, but when you look at ceramic media, you actually have to understand the purpose, what is causing the breakage, how big's the hammer in the attrition collision. And the step change from 8 to 10 millimeters was substantial. And so from this, what we could expect is once you move to 10 millimeters, you're going to have a much more efficient grind. And we'll get to that. When we tested the 4.5 SG media, we put about 2 kilowatt hours per ton, but what we found was it was quite inefficient. And this correlated to what we'd seen in other laboratory-based mills on fixed media loads with the higher SG media. It doesn't net the increased power draw that is generated with the media. It doesn't actually improve the grind. And this is something that you actually need to think about with stirred mills. Increased power draw doesn't necessarily improve to increased efficiency. And so what we found from here after we bogged the mills a couple times, the 4.5 SG media did not work in this scenario with the 8 millimeter media. Now, 10 millimeter media. Now this is the star of the show. What we found was we were able to replicate the same curve as the ball mill, and what we were able to do, it was about 80% less of the energy from what we measured in the field on the day. So an 80% reduction for the same efficiency with the more efficient media as we expected. And this kind of really got us excited and really prompted us, and is what's driven a lot of this push into coarser grinding and why we think we have a pathway through to secondary grinding duties. Now, I'm not going to lie, this was a proof of concept trial. There are things you learn, and there are things you recognize you need to change. And I'm just going to go through the M100 a little bit, but as you can see here, we've got the mill opened. It's a disc-based mill, and what we found was with coarser feed and coarser media, gaps that are normally okay start to become a bit tighter. And so we recognized for future trials we had to reduce the gap between the non-drive end and shaft end cap. So between this and the wall. And with the current dimensions, there is actually a limitation on the size of media you can use. If you look at the rotor, you'll see those square fingers over a screen. There's about a 50 mil gap between the two. If we move to larger media, we actually have to change that back to that rule of your 5 times your largest media diameter type. So, ergo, we have to redesign the screen. The feed inlet, when you go coarser, when you start making small restrictions, things start to block up. As you can see, it was 10 millimeter media, it's 2.5 times the diameter, so we know the feed inlet was too small. Something we needed to modify. And feeding via gravity can be a problem in these duties, and while we recognize that we have to pump the feed in, and if pumping the feed will make things a bit better, but like I said, this was a proof of gravity, proof of concept test. Now, other things. You're sampling from a discharge pan. You're going to get variable feed density and relatively low flow. This is not ideal. I'm not going to dispute that, but this is proof of concept. We want to demonstrate what we can do. And what happened was we had to run a little bit of water in occasionally just to ensure we had flow going through. And to get around this, we just want to pump the feed next time, which logically makes sense. But at the end of the day, this was about proof of concept. And you know what? The concept is proven. So what next? And this is kind of one of the things I'd like to share. We recognize that for the mill to be successful in secondary grinding duties, we need to treat feeds at least 2 to 3 millimeters, F80s, with top size of at least 6 mil. We know that from that trial, we have to trial new components. We recognize the mill has to be slowed down. We also recognize that the discharge screen needs to be redesigned. The motor has a classification effect. That needs to be tweaked. The amount of media getting into the mill has to be tweaked as well. And even slower mills require modified disc designs. And so we recognize that we can do it. Now we have to go through the pathway to do it, and that's what we're doing. And that's what the pathway we're headed on. And like I said, if this is something that interests you, please reach out. We're very happy to come to site and do a secondary grinding trial at your location. So, perfect. So I've gone through the secondary grinding. I know I've explained everything that's involved, where we're headed, but I also wanted to give you a little bit of a side note on some of the stuff we're doing to really validate those larger mills, and that's what the next 2 slides are for. There's been a lot of feedback that people want larger mills, and these larger mills are for the secondary higher throw duties. And we've listened and we've developed designs. We have a larger mill, so here's the 50,000 design on my left. That can hold 50,000 litres, about 8 to 12 megawatts of power. We know that if you go larger, you have to be clever on how you provide aftermarket parts, such as a shell liner or discs, and so we've done things like segmented shell trials to try and further that. We know parts get big, so we've already thought about and got some crazy robotics in to help move discs for you. We recognize this is the fast way. We're developing the parts and we've proven the trials. Stay tuned into this space and you'll see a lot more on secondary grinding and coarser duties from us in the future. Please reach out if you have any questions. Thank you.
And that concludes the webinar. We really hope you enjoyed how IsaMill can cut your secondary grinding energy in half. Now, while that concludes the webinar presentation, we will still be answering questions for a little bit longer. So if you do have a question, please use the Q&A icon at the bottom of your screen and we'll get to your question as soon as we can. If we don't quite get to your question before the end of the webinar time, we will be answering questions later by email. And speaking of that, you'll get a copy of the presentation notes and a link to the webinar in just a few days. Thank you very much for being part of our webinar.